Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Introduce Hai Huang, who's getting his PhD from the University of Michigan, and he works mostly in efficient interfaces to memory and I/O devices, right. Saving power and so on. So I had a good talk with him today about moving data to particular areas of memory and putting the rest of it to sleep. So if you want to go to sleep, you should sit on this side of the room and save power by turning the lights out here. All right. Hi, Hog.
Okay.
Stay headed straight for that side.
Thank you for the introduction. So today I'm going to talk to you about how to boost your system's energy efficiency, performance, and fault tolerance by using these unused system resources in your system. This work is done in collaboration with Professor Kong Shen at the University of Michigan. So we know that for a computer system to do any useful work, it would often require many different hardware components working together. For example, the processor, the memory, the processor cache, the disk, etc. But there isn't any workload that can fully utilize all the hardware resources all at once. So as a result, we always end up having some idle resources in the system. For example, idle CPU cycles, or unused memory or disk capacity, or unutilized network bandwidth. But what most people don't realize is how much of these resources they're actually wasting in their systems. It's actually much more than the amount of resources they're actually using. So instead of wasting these resources, it makes a lot of sense for us to start thinking about how we can utilize these unused resources to our benefit. So to show you how we can benefit from using these unused resources in our systems, I'm going to talk about this free space file system. This is a work I've done recently. And unlike the traditional operating systems, the free space file system is able to actively make use of the unused regions on the disk. And using these unused regions on the disk as a cache, we can improve the I/O performance for disk accesses and also improve the energy efficiency for these disk accesses. And also as part of ongoing work in this project, we're also trying to address some fault tolerance issues for the disk by also using these unused disk regions. But before I describe free space file system in more details, I want to first give you a sense of how much benefits we were able to get under free space file systems. So in free space file system, in terms of performance, disk accesses are 41 to 68% faster compared to static file systems. And despite the better performance for disk systems, the disks are actually consuming less power, 2 to 30% less in this case. And also because we're using only the unused resources, this technique is completely transparent to users and also the applications. So here is the outline for the presentation. I'm going to spend most of my time talking about the free space file system. And towards the end of the talk, I'm going to briefly highlight some future directions. So when we first started working on the free space file systems, we wanted to use these unused disk capacity to improve the I/O performance for disk accesses. But later on, we found that the same technique we're using to improve performance can also be used to address energy efficiency as well. So this is basically killing two birds with one stone, essentially. The motivation of this work actually came from the observation that there is a significant amount of unused disk capacity in modern systems. And this phenomenon there are two things that contributed to this phenomenon. The first is that disk capacity has been increasing at a very fast rate of 60% per year for the past few decades. And also, second, at the same time, price per gigabyte has been decreasing at a rate of 50% per year. So as a result, we have much larger and cheaper disks that can be easily obtained. So users are much less constrained by their disk capacity and are often leaving a significant portion of their disk unused. And to see whether or not this claim is actually true and not just biased because of our personal experience, we've studied these 243 disks in the public server machines in our department. These public server machines are used mostly by undergraduate students doing their coursework and also by graduate students and faculties almost on a daily basis. So these are fairly active systems. So here we show a histogram of the disk usage for these 243 disks. To quickly summarize, we found that 60% of the disks have more than 30% of their capacity not being used, and almost all disks have at least 10% of their capacity not being used. Our observation is fairly similar to the results that were obtained in a previous study done by the Microsoft folks, by Dosser and Blk in a 1999 Sigmetrics paper. So in their study, they studied 4,800 computers' disk usage patterns, and they found that around 50% of the disk capacity was not used to store anything. So from our own observation, and also from this previous study, we can see that in some scenarios, there is a significant amount of unused disk capacity. But unfortunately, unused disk capacity is a complete waste of resources, because if it doesn't contain any valid data, then it doesn't contribute anything to the users. So the natural question to ask is, what should we do with such large amount of free disk capacity? And to answer that question, we first look at the areas where modern disks are currently underperforming. And the first area is performance. Disk performance, a disk have always been one of the slowest components in our systems. And to make the situation worse, disk performance has only increased by 7 to 10% per year, where other hardware components, for example, the CPU and memory, have been increasing, their performance have been increasing at a much faster rate, closely following Moore's law, and in some cases much faster than that. So over time, relatively speaking, disks are actually becoming slower. So disk performance is one of the areas we would like to address. And the second area is power dissipation. Due to the use of these mechanical components in the disk, disks can consume a significant portion of the total system energy. And high power dissipation not only has a negative impact in mobile systems, you can also have these negative impact on large data centers where thousands of disks are being used. So in these systems, reducing power for individual disks can both reducing the electricity cost for powering these devices and also the cooling cost as well. So, so we were asking ourselves, can we actually use resources where modern disks have plenty of, which is disk capacity, to address these areas where modern disks are currently underperforming, which is performance and power. So as it turned out, we were able to do exactly that. And the technique we're using is to use data replication and also take advantage of the unused regions on the disk. So using unused disk regions on the disk and also using replication, we're essentially modifying the disk layout on the disk, which is traditionally the responsibility of the file system. But unfortunately, existing file systems are fairly inefficient when, in making these data placement decisions. The reason for that is that existing file systems rely on these very simple static heuristics. For example, when placing a file on disk, on disk is likely to be placed to another file that's in the same directory, or placing a file's metadata closer to the file's data. So these are fairly intuitive to understand why they're performing better than random allocation, but their usefulness is fairly limited in realistic workload. And to see that, let's look at a simple example here. Here we see we see a set of files under the directory /temp/Linux. Say it's a Linux source code. Using the static heuristics, the file system is able to aggregate all the files within this directory to a single location on the disk. So if all we're doing is to access the file under this directory, say if we do a grep recursively over all the files, then the disk head can be utilized very efficiently because the header doesn't need to move much in order to access all the data on the disk. However, if we have another source code, another kernel source code under /CVS Root/Linux, then if we need to compare the two directories, recursively for all the files. Then in order to do that, the disk head would need to move back and forth between these two regions. And every time you move to a new region, you have to pay these mechanical delays, which is both seek time and rotational delay. And for modern disks, these can be on the order of tens of milliseconds. So we need to minimize these mechanical delays to efficiently utilize the disk. So in the previous example, I gave a very simple example. And there are other examples in real systems that can expose these inefficiencies in existing file systems. For example, if you have multiple processes, and if more than one of these processes are accessing data on disk, if the processes are independent, it's likely that the data they're accessing on the disk is also independent. So the file system is likely to place these data in different regions on the disk. So in order to access or service these multiple processes simultaneously, the disk head will need to move back and forth between these different regions to ensure responsiveness to these different applications. And the same argument can also apply to systems that supports multiple users, because the data that different users are accessing are likely to be placed at different locations as well. So in order to service all the users simultaneously, the disk head will need to move back and forth between these different regions. So if we look at all these examples, the root cause of inefficiency in existing file systems is that existing file systems only rely on these very simple static heuristics when placing data. And when place the data at a certain location, the data's location is never changed. Doesn't matter how badly that disk block was placed on the disk. Or in other words, existing file systems is not able to use runtime information about how the disk is actually being accessed, and using that information to better place the data. So in this free space file system, we're using replication as a technique to allow us to better place the data on the disk and making use of the unused disk capacity. So when reducing mechanical delays, as I said before, we're basically reducing the seek time and also rotational delay. I'm going to show you examples of how to reduce the seek time, also reducing the rotation delay. So in this example, we're looking at the recording surface of the disk from top down. And let's say we have a file called file 1 that's placed at towards the outer cylinder of the platter. And also a file 2 at close to the inner cylinder of the platter. So if we're accessing these two files simultaneously, the disk head will need to move them back and forth between these two regions. And because of the distance between these two files, the seek time can be fairly significant. However, if we notice that file 1 and file 2 are frequently accessed together in this kind of fashion, then we can replicate file 1 to an unused region closer to file 1, closer to file 2. So in the future, if file 1 or file 2 are accessed again, instead of accessing file 1 at the original location, we can use the replica location. So as we can see, the seek time can be significantly reduced because the seek distance is reduced. So reducing seek time is fairly easy by using unused regions on the disk and also using replication as a technique. It has obvious performance benefits, and also it has energy benefits as well, because seeking is a high power dissipation operation. So by reducing the distance, we can reduce the amount of energy seeking back and forth between these related data. So when we're actually replicating data, we're not replicating at a file granularity. We're actually replicating at a block or sector granularity. So in this example, I'm looking at a sector granularity. We have 3 sectors: the blue sector, the red sector, and the green sector here. This example is to show you how to reduce the rotational delay. And the 3 sectors are accessed in the order of blue sector, red sector, and the green sector. In the initial state, the disk head is on top of the blue sector, and the content of the blue sector is currently accessed. It's already read in. So the next thing we have to do is to seek to the track where the red sector is located. You have to pay a seek penalty, then wait for the rotational delay for the red sector to rotate underneath the head. Then the next thing you have to do is to seek to the next track and wait for the green sector to rotate. So the point is that not only seek time is important to reduce, but it's also important to reduce the rotational delay, because rotational delay can also be very significant. So the first thing we try to do to reduce the rotational delay is by using the same technique we were using to reduce the seek time, basically moving things closer to another. So by arbitrarily moving things closer, let's say moving the red sector to a closer location and the green sector to a different location. Now let's consider only the replica of the green sector and the red sector, and not consider the original sectors. So in this case, as you can see, when seeking from the blue sector's track to the red sector's track, the seek time is definitely reduced because we're moving things closer. But as you can see, the rotational delay isn't necessarily reduced because it's very difficult to get this angular distance between sectors correct. And also, when you're seeking to the track where the green sector is located, we also have to pay fairly significant rotational delay as well. So how do we actually reduce the rotational delay in this case? The key to notice is this adjacency thing. So when we notice that the data are related and we are replicating them, placing them together, we need to place them to be adjacent in order to eliminate these rotational delays. So when we're replicating and placing the red sector, we should also notice that the green sector is related to both the red sector as well as the blue sector. And notice this temporal relationship and placing the blue sector, the red sector and the green sector to be adjacent on the same track. So if we're replicating and placing things in this order, we still have to pay the initial seek distance, the seek penalty as well as the rotational penalty for the red sector. But other sectors, we can reduce both the seek time, eliminate both the seek time rotational delay. Instead of only having 3 sectors, you can imagine having hundreds or thousands of sectors being accessed. The performance gain you can get from this technique of eliminating rotational latency by using adjacency can be fairly significant. And also because of the fact that yes?
Is it preferred read-only file?
I'm going to talk about the consistency issues later on. Currently, of course, read-only files can give us more benefits because writing can actually cause us invalidation or updating to multiple locations. Yes?
A couple things. One, in terms of the seek time and reducing the power, as I understand it, the acceleration and deceleration phases are the most expensive.
Right.
Therefore, you're still going to be paying a good portion of the power cost unless they're really, really close together. First of all, have you thought of that or addressed that at all?
So when we're not actually measuring the power dissipation, well, we're actually collecting a disk trace and also using the data spec for the disk to calculate power.
You're going to talk about which disk trace?
I'm going to talk about different disk traces that we collected ourselves.
Okay.
Yeah.
Second thing, are you accounting for cylinder skew and track skew when you're laying stuff out? That is, you may move something in closer, but the fact that you place it too close means you can't seek in time to get to it. You'll miss a whole rotation. And determining track skew and cylinder skew is actually pretty hard.
Yes.
How do you account for that?
We're not actually accounting for that. We're basically using the LBA as a metric for keeping things to be adjacent.
So zero settling
Right.
time.
Right.
Oh, go ahead.
Okay. So in the previous examples, I used replication as a technique to improve the seek time as well as the rotational delay. But using a replication, in cases where we can use replication, we can also use migration. And there are several benefits with migration. First of all, when we migrate data, we don't consume additional disk capacity because we're only keeping one copy of the data. And also because we're only keeping one copy of the data, there's no consistency issue that we have to be worried about. So those are the benefits of migration. But there are some problems with using migration that kind of prevented us from using it. And most of these problems are due to performance. So the first problem is that the replication, when you compare replication versus migration, replication is actually faster because you can think of replication basically as a lazy version of the migration. You don't have to delete the original data after you place the replica to a different location. So in terms of that, replication is actually faster. And the second problem is this reverse lookup thing. So you can't just migrate a data from one location on the disk to another location on the disk because there are other data structures on the disk that actually points to the data that you need to update. For example, the inode structures. So it's very difficult to actually go from the data blocks that you want to migrate to the inode structure. And after you find this inode structure, you also have to walk to various tables looking for the pointer that actually points to this data and update this pointer to the new location. So none of that scheme is currently implemented in any of the existing file systems, which is making this reverse lookup very inefficient. And the third thing, the third problem with migration is that when you migrate data, it actually destroys data synchronicity in some cases. And that can have a negative impact in terms of performance. And I'm going to show you an example of that. So assume we have 6 files under the same directory, and the file system is able to aggregate these 6 files to a fairly contiguous region on the disk. And let's say we monitor the disk access behavior, and we notice that file 2 is likely to be accessed with a set of related files. And we also notice that file 1 is likely to be accessed with its own set of related files. So using migration, we can migrate file 1 and file 2 to these different locations on the disk. So if we see that file 1 and file 2 are accessed with its set of related files, the disk head doesn't have to move much in order to access these files. But what happens if we need to access file 1 to file 0 to file 5 sequentially? For example, if we're copying these six files under the same directory to a different location, we need to pay additional mechanical overheads in order to access these 6 files. So that's the problem with migration. But the same problem doesn't exist in terms of replication, because when we replicate, we also keep the original data block in the original location. So it doesn't matter if file 1 or file 2 are accessed with a set of related files, or accessed sometimes with other files in the same directory. So the point is that a file can be accessed in one kind of a pattern, and sometimes it can be accessed with another pattern. And so using migration, you can optimize for one pattern, but you can have a negative impact for another pattern. But using replication, we can ensure that both patterns can be optimized. Yes?
And the next time file 1 is written, do you validate one of the copies, or do you actually write twice?
We actually invalidate. I'm going to get to the consistency issues in a later slide. So now I want to give you some more implementation details for free space file system in terms of monitoring, replication, and consistency issues. So free space file system is a dynamic file system in the sense that it's able to monitor the disk accesses at runtime. And using that information, we can adapt the disk data layout using that information. And because we're only making use of the unused disk capacity for replication, this is completely transparent to users and applications. And also, this is very different from defragmentation, because defragmentation is still using the static data, whereas in free space file system, we're actually using these monitored disk accesses. So in the free space, when we implement the free space file system, it's based on the ext2 file system, which is a popular file system under Linux. It's essentially ext2 with some added runtime components, with 3 runtime components: the monitoring component, the replication component, and the consistency component. So in a traditional file system, we have this kind of scheme: file system on top of the block device driver, either IDE or SCSI, and on top of the raw disk. What we did was to add a thin layer of monitor that's underneath the block device driver. So any file accesses at a user level or at a file system level can be captured in terms of disk accesses, because we're capturing things at the lowest level. And this information is captured at the monitor. But because at such a low level, we can't make replication decisions, we have to pass this information to the file system for the replicator to make the decisions. Yes?
Block cache in there, right?
Excuse me? Sorry.
So cache blocks in the operating system.
Uh-huh.
And so your behavior going through this, file system access is kind of filtered by behavior cache.
Yes. Yes.
I'm just raising this as a, it doesn't seem like I'm going to get necessarily very clean traces out of this.
We don't want to capture anything that the page cache is already absorbing. We're basically looking at how the disk is actually being utilized with realistic workload.
Okay, so my point is that the behavior of the cache will change over time.
Yes.
If you assume you've got a static workload.
Right. Right. Of course, you can take that into account, so you can simulate different kind of caching behavior. But currently, we don't have that in place. So we're just statically looking at raw disk traces. So after this information is captured at the monitor, this information is actually passed up to the file system level for the replicator to make the replication decisions. The reason we have to do that is because at the low level, at the block device level, we don't know which blocks are actually free and which blocks are actually used. So that's file system semantic information. So that needs to be handled in the replicator implemented in the file system level. And also we have a consistency module that actually straddles between the file system level and the block device level in order to ensure consistency. And we're going to look at why we have to straddle between the two layers. So the first thing I want to talk about is this monitoring level we implemented at the block device level. Because we're actually looking at each individual block disk axes, this provides a fine-grained monitoring. But because we don't want to keep track of each individual block-to-block correlations, because it's too much information to keep, we actually resort to a different strategy to keep these correlation information to ourselves. So we're basically keeping track of blocks that were poorly placed by the file system. And we're going to look at an example here. So on the x-axis, we have the time, and on the y-axis, we have the disk sectors we're actually accessing. So this shows a series of disk sectors that are being accessed over a certain time window. The first thing we do is to divide the entire disk range, disk capacity, into different regions. So in this example, we just divide it into 4 regions. But in realistic file system, you might have hundreds of regions. But the point is to keep, instead of looking at a sector level, we're looking at a region level. So the first thing we do is to choose a target region out of all the regions. And the target region is basically the region with the most amount of disk accesses in the last period. So where you can think of a region where the disk head has spent most amount of its time. So ideally, to reduce or to minimize mechanical delays, we would want to keep the disk head in this target region as much as possible, so we don't have to pay the seek penalty as well as the rotational penalty. So the problem causers in this disk trace is these 3 sectors that are accessed outside of the target region. So basically, we identify these sectors that were accessed outside of the target region and find some unused disk capacity in the target region and replicate them in region 0. So the next time when we have such a disk trace, instead of accessing the original data sectors in the original location, we can access the replicas instead. So we can keep the head in the target region as much as possible. So the monitor mechanism is able to get us a set of candidate blocks that we want to replicate, and also the target region we want to replicate it to. The replicator we implemented in the file system level does fairly minimum number of things. So it basically is responsible for finding these unused disk region in the target region and placing these replicas there. And currently, there are different data blocks in a file system. There are data blocks, there are metadata blocks, and there are various metadata blocks. But currently, we're only able to replicate data blocks as well as inode blocks. We're not able to replicate bitmap blocks and also the super block for reasons I'm not going to talk about in this talk. It's something to do with flushing the hash table from the memory to the disk. And also the replicator we implemented in the file system level is also responsible for free space management. Because we're using replication to consume additional disk capacity, we don't want this to be interfering with users' ability to store additional data. So if we notice that we're low on disk capacity, we're going to stop replication and start invalidating replicas so users don't see everything that goes behind the scenes. So this allows us to make this replication to be completely transparent to users because of this opportunistic use of unused disk capacity. Yes.
Do you include an aging strategy such that you become so comfortable on disk space just with replicas and you can start validating replicas simply to make sure that more replicas that are more temporally relevant?
We do. Right. So in the hash table, we actually keep track of the frequency of use of replicas and also the last time when the replica is being accessed. And those information are used when invalidating replicas on the disk to make. Currently, we're only considering a replica versus user. We don't consider replica versus other replicas in the system.
So once you've used up all the replica space, you won't create any new replicas for any new block.
Yes, right. And because we're using replication, we also have to consider consistency. And to maintain consistency, there are two ways to do that. One is to invalidate the replica when the original data block is being updated. And the second strategy is to update both the original data block and all its replicas. We simply choose the first one because in the second strategy, a single write operation can translate to multiple operations. This is especially bad if the write operation needs to be synchronous. So if the replica has if the data block has 10 replicas, a single write operation can translate to 11 writes to the disk, and those has to be synchronous. So we basically invalidate if we see there's update operation to the data block that has replicas. This consistency module needs to be implemented both at the block device level and at the file system level, because at the block device level we can see which blocks are actually being updated, so we can invalidate when they're being updated. And the reason we also need a part of the consistency module in the file system level is that in some cases you would want to invalidate data blocks even if they're not being updated. For example, if a file is being truncated or deleted, and if any of the data this file has replicas, we don't want to keep those around. We want to invalidate those. So that's why we need to have consistency both at the block device level and at the file system level. And in order to keep track of the replicas, we simply keep a hash table in the main memory. And this consumes fairly small amount of memory to keep track of a large number of replicas. And we also periodically flush this hash table to the disk to minimize the corruption. And also during the shutdown time for the system, we write the hash table to the disk. And also during the system startup time, we read it back to the memory. And also, even with periodic flush to the disk, there's corruption can occur sometimes. So for that reason, yes.
So do you feed that information back to the monitor if a block is getting written really frequently? Tell it, okay, well, stop replicating this. More often.
Right. So our monitoring technique is very simple. We don't keep track of longer history. The case you're saying is definitely true. For a block that keep getting replicated, writing into invalidated, those kind of sequences we want to avoid. But that does require keeping, using additional memory or additional data structure to keep track of that. But that's not being implemented in the existing system. Yes?
Follow up on that question. So there's the cost of replication. There's also a cost of migration, and that's a one-time cost. So again, having an algorithm that can detect if it's a frequent write scenario, maybe not replication, but migration is the right way to go.
Right.
There's a cost of invalidation, and all this stuff is supposed to be costing performance potentially, but definitely in power.
Right.
Are you guys tracking that at all in your experiments?
No, we're actually looking into having a system that does both migration and replication. So you can think of a system that, so in the existing system, we're only doing replication, but you can also add something on top of that to detect whether or not the replicas is actually being used after it's being replicated, or whether or not it's being frequently invalidated after it's being replicated. So after we detect those kind of events, we can simply invalidate the replica. So that essentially is a hybrid between migration and replication.
Also, the follow-up on the append statement you made earlier. Back to the example of file 1 through 6 being a nice in-order stream. Now file 3 gets appended to. What are you going to do in that case? Maybe you've replicated up to 2 different spots, and maybe it's at the end there, so it's fine, you just append to it. But now you got this guy right in the middle, and you appended a whole bunch of data to him. Is there any effort made to actually relocate the stream as a whole, or are you just pretty much toast at that point?
File 3 is the one that's at the original location. It's not being replicated, right? Or are you talking about file 2?
Sorry, I don't remember.
It's one of the files that gets...
That's moving.
Okay.
The one that's being replicated, and now you're appending to.
We didn't look into that kind of things. So in the current strategy, we basically append in the original location. Right. So to avoid corruption in the file system, we also have a set of user tools that allow us to do consistency checking, as well as tools to allow us to format a file system, as well as tools to convert a file system to FS2, basically converting ext2 to FS2 or FS2 back to ext2. And also there are tools for debugging the file system as well. So now I want to give you some results for free space file system. So all the benchmarks are run on real systems with fairly standard PC systems. Has 512 megabytes of memory. It's a standard Pentium 4, around 1.6 gigahertz processor. So the first benchmark we ran was this TPC-W benchmark. It's a transaction web benchmark. We used a MySQL backend database and Apache front end. It's simulating 25 clients for 20 minutes with a mean session time of 15 minutes and a mean think time for each client as 7 seconds. Yes? So the reason we want to use that is because of database accesses. We want to see that for large files, large database files with a lot of these random accesses, how can we actually improve the file system? It was a benchmark that we have in our disposal, so that's why we used it. So these are fairly standard parameters to set up TPC-W. So the first thing we did was to run the TPC-W benchmark under ext2, which we use as our base case. And this shows the disk accesses. On the x-axis, we show the seek distance in order to access that disk. And on the y-axis, we show the access time to access that particular sector. So we can see that as the seek distance increases, we see the rising trend in the access time, which makes sense because longer you seek, the more time it takes to seek. And also for each of the disk seek distances, we see a range of values for this access time. And the reason for that is because of the variability in the rotational delay, which can range from 0 to a full rotation. That's why we see this range here. So for ext2, the problem is these sectors here, which are accessed with fairly long seek distance, as well as these sectors here. So ideally, we would want to have less seek distance, so these sectors are being pushed toward that direction. So
I don't understand the x-axis here. Is that seek distance? So is it any given sector has a particular seek distance, or is that for each data point? How much distance was required to get to that particular?
So we have a series of sectors that we're accessing.
Okay, in trace, series of
in the trace. So we can see the seek distance basically is a difference between these two sectors.
Okay, so some sectors there have very long seeks and yet to very low access time, it looks like.
And
Not a lot of them, there are some of them.
and the reason for that, are you talking about these ones?
Yeah, way down the bottom there, right?
These ones are actually caused by data that's already in the cache. So it doesn't actually incur mechanical delays. So they're directly transferred from the cache to your system.
So these are above the cache traces?
So these are above the on-disk cache, but below the page cache in the main memory, right? Right.
So these look like either 7,200 RPM disks?
Yes. So the range is around 8.3 milliseconds, yeah. So we ran the same benchmark under FS2 and collected the similar trace. And as we can see, the sectors that are accessed from way to the right and also in the middle got pushed to the left. And there are some remains in this region and in this region. And some of that is actually caused by writes to the database as well as to the inodes. Yes?
But it would seem the interesting thing isn't whether you move it to the left or not. The real interesting thing is whether you improve the access time.
Right. I'm not showing all the information here.
I understand there's a power.
Right. So in the next slide, I'm going to show you more detailed information here. So that was the raw data, more or less raw data. So the first thing I want to show you is, what's the benefits to applications. So the first thing we do is to measure the average response time for ext2 and FS2. As we can see, under FS2, because of the better data placement on the disk, there is a 34% improvement in the average response time comparing FS2 and ext2. And most of that response time is due to faster disk accesses. And here we break the disk access to its various components, the seek time, the rotational delay, and the transfer time. So we can see that both the seek time and rotational delay are reduced under FS2 because things are closer to one another on the disk. When we ran this workload, the worst case replication overhead is only less than 2%. And the reason for that is when we're writing replicas on the disk, it doesn't have to be asynchronous. So we can buffer a lot of data and write in batches. So that minimizes the overhead due to writing. And the total energy saving in this case isn't too great. It's only 7%. And the reason for that is TPC-W runs for a fixed amount of time of 20 minutes. So the idle time that we converted, we were able to obtain, are not used for power saving purposes. So we can think of this technique as a way of getting additional idle time. So it can be potentially be complementary to traditional power management techniques to the disk, basically taking advantage of the idle time. So the next benchmark we ran was a CVS update benchmark. We're also comparing ext2 versus FS2. So in this benchmark, we basically do a CVS update in a CVS repository that contains the kernel source tree. Under ext2, the runtime is around 33 seconds, whereas under FS2, we can improve it around 30%, reduce the runtime for this CVS update operation. We also show the per access time, as well as a breakdown between the transfer time, rotational time, and the seek time. In this workload, the total energy savings is around 31%. So besides these two benchmarks, we also ran other benchmarks. One of them is a StartX, basically loading the X server and also starting a Windows manager. So in that case, we improved the load up time by 16%. And there's another workload we use with a surge. It's fairly likely the TPC-W workload, but with the static data. It's 18% faster in the average response time for the clients. And the last thing we did was to measure the system boot up time. By using FS2, we're able to reduce the boot up time by 2 seconds, where the normal boot up time is around 18 seconds in the system we were using. just to quickly summarize, using FS2, we were able to get some benefits, fairly significant benefits in terms of performance as well as energy. And the best thing about that is that it doesn't cost users anything to get these kind of benefits. And we made the software available if you're willing to try this on your system. So as a part of ongoing work, we're also trying to address some fault tolerance issues by using data replication. On multiple disks, we already have existing solutions basically using RAID to provide additional parity information so we can sustain additional failures. But what happens on a single disk, for example, those that are on your laptops or PDAs, because of form factor constraints, you just install another hard drive in there to increase the fault tolerance of your disk. So is there any way we can do better than basically nothing? So the thing we're thinking about is to use these data replication to replicate important data on the disk to other regions on the disk, and using these platters and cylinders as natural protection boundaries. So basically, if you have important data on one of the platters, you can replicate it to a different platter. So hopefully the head crash that causes you losing the original data at the one platter doesn't affect the replicas. So you can still recover from that. But the challenge here is this failure characteristic. So after a head crash, what exactly happens on the platter? Does it just affect a single location, affecting a few sectors in the neighboring tracks, or just single track? Or does it affect an entire track at a time? Because after the initial crash, the head can be dragging around the track for a few more rounds, so that can destroy a lot more sectors. Or does it affect a cylinder of sectors, because a head can also causes vibration in other heads, so that can cause more extensive damage to the surface. Or does it only cause damage on the same surface, but at random locations on the same surface? So these failures, what we call localized failures, can be addressed fairly simply by placing data at a different physical location on the platter. But there can be random failures. For example, the initial impact of the head to the platter can cause its debris, and these debris can actually cause a chain reaction of other failures on the platter itself. So more or less random failures. So how do we address those kind of problems? Yes?
Yeah, two things. One, do you have any data in regards to how often a head crash occurs that you actually have a disk that survives?
We don't have that kind of information. So
my suspicion is very low.
Yeah.
Second of all, and this is something that I kind of hope we can get to, but everything you're doing is requiring knowledge of how the data is laid out in the disk. That is extremely difficult to determine on some random disk. Anybody. The multi-zone layout, the spare sectoring. I mean, it's really, really hard to determine the layout of the disk.
There are tools that allow you to do that, right? There is some work done.
I'm telling you, it's very, very hard.
Right. Yes, I understand. Yeah. But there are tools to approximate those kind of things. You don't have to be exactly right, in order to get these kind of benefits.
But the disk knows roughly.
The problem is when you're laying out stuff at the file system level, and file system doesn't have a clue where the data is, especially if it's arrayed below it, because it has no clue that it's an array.
Right.
So now you're laying stuff out, and you don't even know what platter.
Right. We're currently looking.
is going on.
We're currently looking only at the system with a single disk, so we're not touching at the RAID level. So
The problem is you don't know if it's a single disk or
Right. So the problem here is that we need to really characterize what exactly happens after a head crash, and also whether or not, how do we actually replicate to maximize fault tolerance, basically minimize the chance that the original data blocks and replicas are simultaneously destroyed. In that case, you're basically permanently losing your data. And also, how do we determine which data to replicate? Do the users actually give hints to the file system, or do the users actually mark a directory to be important, or what's the strategy to do that? So there is some future work besides this disk work I've done. So in the disk work, I've addressed the power problem, the performance problem, as well as fault tolerance problem by using these unused resources in the system. I've also done some work in the memory subsystem, basically identify these unused or unmapped memory pages, basically some other unused resources to address power. So we have solutions, pure software-only solutions to address power, as well as some architectural solutions to address power. But besides memory and disk, there are also other hardware components in the system. For example, the video card, the sound card, network card. These hardware resources are definitely improving very rapidly in recent years. So we need to start thinking about how do we best take advantage of these resources in these hardware components. Just to give you an idea, for example, in the video card, it has a very powerful processor. It has a 650 megahertz general purpose GPU and has a very large amount of memory. So other than when you're playing a game or doing CAD work, you're not actually taking advantage of that resource. So how do we take advantage of that? And also, you can also ask the same problem with the network card and sound card as well. So there are some examples of how do we harness or benefit from using these unused resources. One of them is to aggregate these buffer pools. So in addition to the main memory you can use for your page cache or your application data, you can also use the memory in the video card as well as the memory in the network card. And another example is to aggregate these processing elements. For example, your CPU, the GPU, and the network processor, the sound processor. The challenge there is that you have to consider all these different architectures. There's a lot of architectural challenges as well as the compiler challenges, runtime challenges. So it's a very simple problem to address. And I'm oversimplifying this problem here. So as a conclusion, I talked about this free space file system and also talked about how to use unused resource, unused disk capacity to improve performance as well as energy efficiency. But the point to take is there's plenty of other unused resources in the system. So we shouldn't just target our effort into resources that are actively being used, but also those resources aren't being used because hardware is definitely becoming more powerful. And currently, this is a fairly large problem space and fairly unexplored. So that concludes my talk. Yes?
3 projects I'd like to see if you're aware of and have perhaps thought about how they might impact some of pretty current. So first of all, the pre-block scheduling work by Jerry Schindler at CMU.
Right.
You take a look at that and see how that might be incorporated into your
we're aware of that, but in their work, basically, they're using these rotational delays to do actual work.
Right.
Potentially, when we're replicating, we can also use the same tech to minimize the replication overhead. But the problem is that even in the worst case for the TPC-W workload, the replication overhead is already fairly small, less than 2%. So the additional benefits of using free block scheduling, it's fairly minimal, I think.
The second one is the super fetch work.
The
super fetch work from Microsoft.
I'm not aware of that.
Basically, the way it affects your stuff is it actually detects when your stuff is like during boot or during an app launch that's in order and relocates it so it's all in a nice launch stream so you don't have any delays. So it's very much in the same line as what you're doing, so you might want to take a look at that.
So it's using migration only, right?
Yes.
It's migrating things.
It's migrating based
Okay.
on boot and app launch.
Okay. Okay.
The third thing is the hybrid disks, or putting NVRAM on disks. That's going to be extremely common. And that's going to definitely reduce the impact of migration and replication because if you've got a gigabyte of NVRAM on the disk, which isn't unreasonable at all, that's going to eat into the impact of migration and replication. I'm not trying to say don't do what you're doing. I'm saying, is there any way you can sort of roll with the punches a bit? Say, okay, this is going to happen. Here's what my algorithm should then change. Something to consider at least.
Okay. All right. Other questions?
Maybe just a follow-on to that question.
the system we used has a fixed size of buffer cache, so we didn't look at the other buffer caches sizes. So I guess the one thing we can do is to get rid of the buffer cache and collect the disk trace at the lowest level, so that captures everything. Then later on, we can use that raw disk trace to simulate different buffer cache strategies.
So, do you run this on your Linux box?
No. It's fairly stable currently. It's fairly stable, but I'm not running it yet. Yeah.
So the storage of the metadata for the replica. Okay, so you put it in a hash table?
Yes.
Okay. Want to talk a little bit more about the details? You kind of glossed over it.
So the hash table, it's fairly small. It's around 8 kilobytes per 1 gigabyte of replica on the disk. So we keep track of the block number, the replica's block number, as well as the timestamp, when it was last accessed, and also the frequency when it was accessed. So it's a fairly small data structure that we keep in the memory subs.
And it's integrated with, it's got infinite knowledge of free information.
Excuse me?
So it has infinite knowledge, of course, of all the free information.
Well, at the file system level, we know exactly which blocks are actually free and how much unused disk capacity is in the file system.
I guess I was wondering, so it seems like one of the places where this much is complicated is making sure that there's consistency between the hash table and free blocking.
Right, right. So the current strategy is basically, if it fails, then it's kind of like using fisking during the next boot up time. So if we don't see any inconsistency, then that's fine. If we see inconsistency, our user level 2 is able to invalidate some replicas and update hash table. So the next time they boot up, everything is in a clean state. But there should be, we'll start thinking about more complicated strategies of changing the file system's metadata structure in order to keep track of not only the original data block, also the state of replicas as well. So that can decrease the fisking time at the next boot up time.
So when do you flush the hash table?
It's basically every minute right now.
And is it coordinated? Is it done the same as the flush of free block?
No, these are two separate kernel threads that control those.
That worries me.